So hello everyone, today we'll be discussing the integrated rate law. So it's a very easy concept and the applications are usually straightforward and simple, but you need to understand the concept very well in order to be able to solve these applications. So just to start, what is the integrated rate law? The integrated rate law is basically the use of integration techniques to find like expressions with integrals in order to be able to plot a graph or to find like specific concentrations at specific times or vice versa in order to basically get more accurate results. So we're going to be discussing the integrated rate law for three different orders: the zero order, order 1, and order 2. Now the rate laws have been discussed in previous videos, so I'll just fill them in right now. So the rate law for order 0 is r is equal to k, the rate law for order 1 is r is equal to ka, and the rate law for order 2 is r is equal to ka squared. Now, the main focus on this video will be solving for the integrated rate law, plotting the graph with the expression we got for the integrated rate law, and finding the half-life also using the integrated rate law that we got. So to start, we just need to remember that rate is basically the concentration of d concentration of A over dt, and there's a negative here because the concentration of a substrate actually decreases by time because it's being used up. And so we're gonna get that R is equal to negative dA over dt, and then we can equate that to the rate law we got previously. So we say that negative dA over dt is equal to k. Now we have to solve for A, so we isolate A on one side. So we get dA is equal to negative k dt. We integrate both sides with limits, and on this side we use limits A initial to A. And so we're gonna get that A minus A0, since the integral of dA is A, we get A minus A0 is equal to negative kt. Solving for A, we get that A is equal to initial concentration of A minus kt. Now for plotting the graph, we find out that it's actually a negative slope because k is always a positive. The rate constant is always a positive number, and so that negative number indicates that it's a negative slope, and it's clearly in the form of y is equal to mx plus b, so it's a linear line with a negative slope. Now moving on to half-life, what we need to remember before we go on is that at half-life the concentration of A is actually equal to the initial concentration divided by 2, because that's when half of the initial concentration has been used up. And so we say initial concentration over 2 is equal to A initial minus kt. This time we solve for t, since half-life is actually a term in terms of seconds or hours or minutes or whatever, it's in terms of a unit of time. And so we solve for t. We take A initial over 2 minus A initial is equal to negative kt. We divide by negative kt on both sides, and you're going to end up getting that t is actually equal to A initial over 2k. And that's your half-life for zero order. So that's basically it for zero order. That's all you need to know for zero order. We'll be solving applications in a separate video. Now, moving on to rate law of order 1, the integrated rate law of order 1. We're going to follow the same steps. We're going to equate the original or the general equation to the equation we have in the table. And so we get negative dA over dt is equal to ka, and then we're solving for A again. So we get dA over A is equal to negative k dt. We integrate both sides, and we get that we take the negative k as a common factor outside because it's as a constant, since it's a constant. And then we get that since here it's dA over A, it's basically like integrating dx over x, which is ln x. So here you get ln A minus ln A initial is equal to negative kt. Now, again, solving for A on one side, you get that ln A is equal to ln A initial minus kt. Now, moving on to the half-life, I'll keep the graph for the end because there's something about it. Moving on to half-life, what we do is that ln A initial over 2, we substitute A for A initial over 2. Ln A initial over 2 is equal to ln A initial minus kt. Here we're going to separate the ln into 2. So it's going to become ln A initial minus ln 2 is equal to ln A initial minus kt. Canceling ln A initial from both sides, or minusing ln A initial from both sides, we're going to get ln 2 is equal to kt. And so we get that t is actually equal to ln 2 over k. Now what is special about this half-life? It's actually a constant half-life, because ln 2 is a constant and k is the rate constant. So this half-life is actually a constant half-life, and that's why it's the most commonly asked in most questions, because it's the applications is there's a lot of applications that you can apply knowing that it's a constant half-life. Usually, to find out if it's first order, either look at the unit of k that they give, which is always time -1, so seconds -1, minutes -1, so on. Or they're gonna mention that it's a radioactive sample, or they're gonna mention that the sample is decaying, or so on. So if they mention any of these three things, that means it's first order and it has a constant half-life. Now, plotting the graph, if you plot ln A against t, again, you're gonna get a linear line with a negative slope because of the negative line found here. But what if you plot A against t? If you plot A against t, you're not gonna get a straight line. You're gonna actually get a curve. But when you get a curve, if you want to find out if it's half-life or not, if it's first order or not, what you can do is check the half-lives. Check 2 consecutive half-lives. So check, let's say, from 20 to 10 and from 10 to 5. If from 20 to 10 it takes around 10 seconds, for example, and from 10 to 5 it also takes 10 seconds, it means it's a constant half-life, which means that it's a first order reaction. But if it's, let's say it's from 20 to 10 it takes 7 seconds, and from 10 to 5 it takes, 12 seconds, that means it's not a constant half-life, so it's not first order. So that's basically it for first order. Now, moving on to the last one, which is second order, we do the exact same steps. We get the general equation, we equate it to the rate law, and then we solve for A on one side. We get dA over A squared is equal to -k dt. Integrate both sides, you're gonna get the integral of dA over A squared is basically -1 over A. So you do -1 over A, like substitute in the limits, you do -1 over A minus -1 over A initial, so it's positive. -1 over A plus 1 over A initial is equal to -kt. Now solve for 1 over A actually. You take 1 over A initial to the other side, it becomes a negative, and so the whole equation will be negative, so you can just cancel the negative out. So you get 1 over A initial is equal to 1 over A, is equal to 1 over A initial plus kt. Now this is the only equation or the only order that has a positive slope when graphed, and it has a positive next to the k and not a negative. And now for the half-life, we follow the same steps. We're gonna substitute this A for A initial over 2, making it basically 2 over A initial is equal to 1 over A initial plus kt. Take all A initial to one side, you get 1 over A initial is equal to kt, and then you get T is equal to 1 over Ka initial. And so that's your half-life for second order. And that's basically it. Now, this table basically summarizes everything for the three orders. They usually won't ask you for the proof of the integrated rate law, but there's going to be a lot of questions about the half-life, and they might ask you for the expression without asking you to prove it. And so this is basically a summary of everything, and there will be applications in a separate video. If you want to find the separate video, just go on our channel. Make sure to subscribe to find other subjects, either chemistry or the other subjects. Thank you.